So that's big O notation and its siblings. Um, and now that we have all of that, now that we have all the discussion underway, and now that we've defined some basic stuff, uh, I can define my first time class. So here's an important definition. Here's a big step in our development of the theory. Um, define. I've already written the definition. Time in all caps of f of n. This is going to be our first real complexity class. It's equal to the set of all decision problems which are decidable by Turing machines operating in time O of f of n. So finally, we're starting to come up with categories of difficulty. Time f of n. So that what it's the set of all the decision problems that are decidable by Turing machines operating in time O of f of n. So comparable, so operating in times that are comparable to f of n. That's our time classes. Um, Now I would like to immediately jump over to space, but maybe, you know, to excite people, I should probably define a couple of important time classes. So the two most important time classes for our purposes later on, we're not going to be dealing with them immediately, are, of course, the fabled P. The P is equal to the union, k equals 0 to infinity, of time n to the k. And so really what this means is it's the class of problems solvable in polynomial time, right? If you're n to the k for any k, it's the union of all of these different time classes. And so what this is going to function as later is this is what we're going to view as the set of all problems that are computable efficiently. Um, in some sense that we'll get into later, P is the class of problems which are not just computable, but efficiently computable. And so that's where the importance of P comes from. Uh, I guess the other important time class is exp. This is much less important. Exp is sort of the out of bounds class. If you are talking about exp, if you have a problem in exp, then you glitched out. You glitched out of the map. Something went wrong. uh, 2 to the n to the k. So you still have this polynomial n to the k. It's just the power of 2 now. So these are really, really bad algorithms. Of course, it includes all of P, but like this is a monster class compared to P. Um, but in terms of what we care about, it's really these are the two main time classes that we're going to be considering. But for now, I really did need to stare at this. We did need this to go on in some of the more basic results. So that's the time classes. And now let's define the space classes. So now I want to talk about space. So how do we talk about space? Well, what I want to note is that, first of all, consider the the algorithm for addition. Let's just think about this for a second before we talk about space. So here's like 349, 67. Let's add these two numbers and think about the space that we're using. First of all, just the setup here. And actually, let's compute it first. So we add 9 and 7, we get 16. And I'm going to put a bit here. Right, we need a carry bit effectively, right? And then I add 6 and 4, and I get 10, I get 11, and then I get a 4 here. And there it is, there's the computation. Now, here's a question. What here counts as space use? Does the input and the output count? First of all, obviously this doesn't count. Let's kind of no, no, don't matter. So obviously this plus sign and line are just there to kind of frame this, but in a computer we don't need these two things. These aren't vital to the computation in any sense. The input and the output, the two numbers as the input and the one number as the output, those are essential, but should those count as space use? Well, they could. I mean, that would be up to us. But if we did that, then we would kind of lose some specificity because if we included, let's go ahead and say it like this: if we include input and output as used space, then this algorithm would operate in space O of n. But is it really space O of n? Really? How much space did we actually use? We used 2 bits. This is the only vital thing that we really had to do. And this is independent of the input. This is independent of the input length. Well, kind of, right? We might need a number of inputs that are like the logarithm, I guess, of the number. Well, I guess if we're thinking about the number as a number of digits, it's sort of still O of n. But we only really need one carry bit, right? Think about it like this. In fact, when I did this algorithm originally with you guys, when I did a video that showed how this algorithm would work on a multi-string Turing machine, I didn't even use carry bits at all, right? We had a state for it. But instead of thinking about that, let's just think about like a single bit. Suppose I just had a box here where I included the carry bit when I needed it and erased it and put a 0 there when I wasn't using it. I only really need one bit in order to do this addition problem besides the input and the output. I only need a single bit of actual space, like scratch paper. I only need a single bit, a single cell of scratch paper to do this. So I could say that the input and the output are space use, but then I would get an O of n algorithm when it's pretty clear that this algorithm is faster than that in terms of space. I shouldn't say faster. Really, this should be space O of 1. It should be space O of 1, and if I include the input and the output as space use, then I don't get that. So the conclusion is that we shouldn't we shouldn't count the input and output as used space. We need to kind of revise our formalism a little bit to make sure that we don't count the input and the output as space. And so here's how we're going to do that. So we're going to make use of our multi-string Turing machines to define a special kind of Turing machine in order to define space usage. So here's a definition. A Turing machine with input and output is a 3-tape machine. So it's a 3-tape Turing machine. It's a multi-tape Turing machine uh, with the following extra properties. Let me actually go ahead and say it like this: with the extra property, with the extra restriction that the input tape. And remember, when I have a multi-tape Turing machine, it's always interpreted that the first tape is the one with the input at the start, and that the last tape is the tape with the output at the end. So we already implicitly, just by saying there's a 3-tape Turing machine, we already have an input string and an output string. But we're actually adding an extra restriction. We want the input tape. We want to make sure that the only tape that's being used so that we can keep track of it is the middle tape, the work tape. So we have like a work tape and then 2 other tapes that hold the input and the output, and then we can keep track of space by only looking at the work tape. So it's a 3-tape Turing machine with the extra restriction that the input tape is read-only, and the output tape is write-only, i.e., only allowed to do work on the middle tape. And I could have defined this as a multi-tape Turing machine. I could have had more than 2 work tapes. It doesn't really matter. Um, but we only really need a 3-tape Turing machine. So more formally, let's kind of formalize this and see what we need to say about the 3-tape Turing machine to get a read-only input string and to get a write-only output string. More formally, uh, so let's think about this. So let me draw some tape. So I'm only allowed to read this, and I'm only allowed to write on this. Um, so let's think about the transition function, delta. Well, delta is a transition function defined for a 3-tape Turing machine. So it takes 3 symbols, sigma 1, sigma 2, sigma 3, and also a state q, and it returns as an output um, a new sigma. I guess not a new sigma. I should use a different Greek letter. How about lambda? Lambda 1, and also direction, right? A d1, lambda 2, d2, lambda 3, d3, and then also finally a new state p. So what needs to be true about this transition function in order to have the input tape be read-only and the output tape be write-only? Well, if the input tape is read-only, well, then what does lambda 1 have to be? This is the symbol on the first tape, right? So I'm like right here, let's say. This has to be the same if it's read-only. So in other words, I'll call this the first point, sigma 1 has to equal lambda 1. This creates read-onliness. I'm only allowed to read the input tape. I can't actually replace the symbols with anything else. And 2, I need the output tape to be write-only. And so how do I make sure that the input tape is write-only? Well, that's going to have to do with the direction, actually. This D3 right here. If I make sure that D3 is never -1, then I essentially can't move backwards. I can't read what I've written. I can only move forwards. That's the idea. And so this is actually what's going to make the output tape write-only in function. So a Turing machine with input-output is basically a 3-type Turing machine with a couple extra properties that make it guaranteed that all of the work that's worth looking at, all the actual like computation, happens on this middle tape here. That's the important point, and that's going to help us define space complexity in which the input and the output don't count towards the space complexity. So let's go ahead and finally use this to define space classes. So let M be a a Turing machine with input-output, and suppose m halts on input x after t steps. Now, I want us to be very clear about something that will come back up later. It's very technical, but I want to make sure that we've stated it very clearly for the record, which is that space complexity, the entire idea of having space being used, is contingent on it halting, meaning that the time space complexity is not defined unless time complexity is finite. So if the Turing machine does not halt, then space complexity is not defined. Okay, so I cannot talk about the amount of space used in a computation unless the computation halts. That's going to be important later. Um, a little bit important. It's important to me as a theorist. Um, so okay, so since there's t steps, I can enumerate them. So for L equals 0, 1, 2, dot 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 L up to t, I should say. So I'm going to enumerate the steps 0 up to t, where 0 is the well, it's not really the steps. What I'm going to enumerate is the configurations. Let CL equal the configuration after L steps. Be the configuration of M after L steps, i.e. CL, let's go ahead and write these out, is equal to what's a configuration look like for a Turing machine that has 3 strings? Well, we've got 3 strings, so we've got 3 tape configurations. We've also got 3 integers that represent cursor positions. And then finally, we've got a state queue. So that's our configuration. Define the space used by M on X as the maximum of this middle work string, right? The middle string is the one we care about. The tape configuration here and here, we know what these are going to be at all steps. Only T2 is going to change. And so that's what we're going to do. We're just going to take the maximum length of this string over the entire computation for L equals 0 to T as our amount of space used. So it's the maximum at any point in the computation. I might erase everything, but God remembers. So it's the maximum for L equals 0 up to T of the length of T2. It's the most tape that I use at any point in the computation. The max amount of tape used at any step, at any point in the computation. So that's the definition of the space used. And now we can define all the other stuff in the same way that we did the time stuff. So we say that M operates in space f of n if for all inputs x, M uses space at most f of n, f of the length of x, I should say. Underline this. And then finally, I can go ahead and finally say define space f of n to be equal to the set of all languages which are computable by Turing machines operating in space uh, O of f of n. So it's exactly as it is for the time class, remember. So time f of n is the set of all decision problems which are decidable by Turing machines operating in time O of f of n. Space is the exact same thing, but for space. And we'll finish up, I guess, by defining, uh, just as we did for time, the two most important space complexity classes. So two most important. So I'm going to define L. L is a very, very special special class. It's equal to space log n. Base of the log is technically 2. Doesn't really matter. Log space is actually going to be pretty important for us, arguably the most. And then we've also got p space, which is exactly what it sounds like. It's p, but for space. Union k equals 1 to infinity of space n to the k. I guess I started with 0 for time for p, so let's go ahead and make this 0. These are the two most important space classes. So we've got, I think I defined 4 extremely important classes today, actually. Yeah. P, exp, L, and p space. A lot of what we're going to do involves these 4 guys. There's a few more to define that are kind of the gang. Maybe I'll just draw the simple picture for now and then end it here. So here's R, all the computable functions. And then here's L. L is going to be contained in P. P is contained in exp, of course, but it's also contained in P space. P space is contained in exp. And exp is contained, of course, in R. So, I mean, we haven't proven this yet, but this is what the picture looks like. Oh, shit. There's a few more important guys to define, actually. I should probably define NP. NP is going to end up right here. And then there's also going to be co-NP, which is pretty important in its own right. And this is kind of the central family. Really, actually, it's in terms of complexity theory, the focus is on P space and what's inside of it. But this is our first kind of broad overview of a hierarchy. And there's much, much more to say here. There's a lot to say, but this is sort of the beginning of the picture that we're going to be drawing. So thanks for watching, and next time we will start to really get into it in terms of proving things.